This is going to be a video on section 4 of chapter 6, which is about getting into rectangles here. So parallelograms, like I said, are the basic shape of quadrilaterals. So they're kind of like the parent shape. And aside from triangle, or aside from kites and trapezoids, they're basically kind of like the parent of the other quadrilaterals we're going to be going into. So the first one up is a rectangle. So a rectangle is basically a special type of parallelogram. So that's what I mean when I say parallelograms are the parent shape, and then rectangles and rhombuses and squares are all different types of parallelograms that have special feature on them. So a rectangle is defined by the following properties, and you'll notice that of these, 4 of them are the same for a parallelogram, because as I said, a rectangle is a parallelogram. The only one that's different is the first one. So the first one says in a rectangle, all 4 angles are right angles. So remember, a right angle is 90 degrees. So a rectangle is basically a parallelogram where all 4 angles are 90 degrees. And then everything else is the same as a parallelogram. So opposite sides are both congruent and parallel. Remember, this is the symbol for parallel, and this is the symbol for congruent. Opposite angles are congruent, and consecutive angles are supplementary, which means that they add to 180. Now, these two are kind of moot because if all 4 angles are right angles, then these two kind of follow anyway. And then the diagonals bisect each other. They also do something else, but we'll get to that in a second here. So again, here's a rectangle, and we all know that opposite sides are congruent. So congruent there, congruent there. We know that they're parallel, para, 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 and we know that all 4 angles are right angles. Right? And again, that means that opposite angles like this angle here and this angle here, those are going to be congruent because they're both 90 degrees. And consecutive angles like this angle here and this angle down here, those are going to add to 180, which is what it means to be supplementary. So again, these two are kind of coming from the fact that everything's a right angle anyway. Now, like I said, number 1 here is kind of like the thing that defines a rectangle. Again, another way of saying a rectangle is a parallelogram with all right angles. Because from 2 to 5, all those rules are the exact same rules for a parallelogram. Now, a rectangle has a special property about it too. Whoops, sorry about that. In that in a rectangle, the diagonals are also congruent to each other. So in a rectangle, this diagonal right here that I just drew, this diagonal right here, is going to be congruent to this diagonal right here. So these two diagonals are going to be the same distance or the same length. Now the converse is also true. If you have a parallelogram and you can prove that the diagonals are congruent, then you can say that the parallelogram is a rectangle. So that means, again, the difference between these two is what do you know. In this first theorem here, if you know it's a rectangle, then you know the diagonals are congruent. Whereas this one here says if you know it's a parallelogram and the diagonals are congruent, then you can say it's a rectangle. So it's a matter of what are you trying to prove. You use this reasoning when you want to prove that something is a rectangle. You use this reasoning when you want to prove that the diagonals are congruent if you already know that that something is a rectangle. So let's use them in a proof here real quick. So given that this is a rectangle, prove that these two triangles are congruent. ADC, which is this triangle right here, ADC, so that's my first triangle, and then BCD, so BCD, that triangle right there. So we're going to do this in 2-column format. This is going to be my given, so right there's my given. There. And then we want to prove that ADC is congruent to BCD. So again, if we want to prove that two triangles are congruent, we have those 5 theorems. Side, 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 angle, 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 side, and the hypotenuse leg. So those are the 5 ways we can prove triangles are congruent. So that's what I'm trying to get out of this shape here. Let me erase some of my squiggles there. So since it's a rectangle, I know a few things. Because it's a rectangle, I know that opposite sides are congruent. So I know that AD is congruent to BC. And because those are both pieces of these triangles down here, it might be something to worth note. So I'll say that AD is congruent to BC. And the reason I know this is because you just say opposite sides of and I'm just going to draw a picture here of a rectangle. That's usually how I denote a rectangle. Of a rectangle are congruent. Just saves me some wording there. So I know that those two sides are congruent because opposite sides of a rectangle are congruent. Now, because it's a rectangle, I also know that the diagonals are congruent. So I know that AC is going to be congruent to BD, because that's one of the properties of a rectangle we just talked about over here. That if it's a rectangle, then the diagonals are congruent. So I'm going to be using this reasoning here because I know it's a rectangle that was given to me, and I want to state that the diagonals are congruent. So the then part is what do you want to state. The if part is what do you know already. So I'm going to use this first one here, not the second one, because the second one's backwards. The second one says if you know the diagonals are congruent, then you say it's a rectangle. But I want it the other way. I know it's a rectangle. I want to say the diagonals are congruent. So I would say that AC is congruent to BD. And the reason I would this would be saying that the diagonals, I'll put diag for short, diagonals of a rectangle are congruent. That's that. So I now have that AC is congruent to BD. Okay? So I'm pretty close to side, side, side right now. I have two pairs of sides, AD and BC, and then AC and BD. So I have two pairs of sides congruent already. If I can get a third side, I can do side, side, side. Well, the third side would be this last one here, DC, because it's ADC and BCD. Those are my two triangles. So DC is the last side. And if you look here, DC is in both triangles. We have ADC and then we have BCD. So they both include this bottom part here of the rectangle. Both triangles have that as one of their pieces. So I can say that DC is congruent to DC by the reflexive property. Oops. Remember, if you want to say something's congruent to itself, you use reflexive. Or put another way, if something is a piece of both shapes and you want to say that it's congruent to itself, you use reflexive. And now, as I said before, we can end this with our proof statement that ADC is congruent to BCD because of side, side, side. We have three pairs of sides that are congruent, and so we know that they're all congruent because of side, side, side. So that's how you would use, again, one of these theorems in a proof here. So we use the top one in this case because, again, we knew it was a rectangle that was given to us, and we wanted to use the fact that since it's a rectangle, we know the diagonals are congruent. So that's why we use the first statement rather than the second one. Again, there's no real name for these theorems, at least none that I know of, so I just usually write out what the theorem is anyway. So it's not really that big of a deal to again, know the proper names or whatever. As long as you know what the theorem means and you can write down the definition of the theorem, then we're good. So that's why I kind of wrote down this definition, this entire definition here, in my own sort of lingo right here. Okay? So I obviously abbreviated some wording there, but that's okay. Now let's get to some of the algebra of this too here. So remember, one of the properties of a rectangle is that the diagonals not only are congruent, but they bisect each other. So this is saying is if DE is 8x minus 7, so 8x minus 7, that's DE. EB is 3x plus 13, so 3x plus 13. What is the value of x? Okay, so if these are the diagonals of a rectangle, and again, I know that the diagonals bisect each other, that means I know that these diagonals cut each other in half. Well, okay, if they cut each other in half, that means that this half has to be congruent to this half. So 8x plus 7, or 8x minus 7, has to be equal to 3x plus 13. Because again, they're both half of the same piece. So again, you go through and you do your normal math here. So minus 3x, minus 3x. We get 5x minus 7 is equal to 13. Add 7, add 7. We get 5x is equal to 20. And then divide 5, divide 5. We get x is equal to 4. Now, if they asked you for the length, you would plug 4 back in and figure out the length of each segment if you needed to. But again, the diagonals bisect each other, and they're not only that, but they are also congruent. So those are the two properties about the diagonals of a rectangle you need to know. They're congruent to each other, and they cut each other in half. So here it says BDC is 4x plus 12, ABD is 6x minus 8, find the value of x. So this right here, BDC is 4x plus 12. And ABD is 6x minus 8. So find the value of x. Okay, so what we're going to do is we're going to think about this here and say, okay, I know that since this is a rectangle, which I didn't put down here, but we can assume this is a rectangle. I'll preface that with this. If we know that this is a rectangle, we know that the opposite sides are congruent and that they're parallel. So we know that AB is parallel to DC. Well, hold on. If I have parallel lines, that means I have corresponding and or alternate interior angles that could possibly be going on here. So I'm going to look for those alternate interior angles because of that Z format and see if I can't find any. So let me start with this line up here. I'm going to travel down this line, get to the end, take a tour down the transversal, which is the line that connects these two, and then go down the other line. So I get that Z pattern. And I know that the corners of this Z are congruent angles. So that means that this right here is congruent to this angle right here, which again are the two angles I'm looking for. So I know that 4x plus 12 is going to be equal to 6x minus 8. And once again, you can solve this with basic algebra rules. So minus 4x, add the 8 to get rid of minus 8. I'm kind of doing multiple steps at once here just to shorten down the video time for those of you that needed this in a hurry. And then divide by 2, and you get 10 is equal to x. And that's that. So once again, not too different than what we've been doing in the past. We did this a little bit with parallelograms too. Just make sure that if you're ever kind of wondering about this angle stuff, don't forget about the alternate interior angles because it's one of the angle types that a lot of people miss. So don't be afraid to draw that Z pattern and see if you can't find something in there. Now, this last little bit here is probably going to be the bulk of the difficulty here. So if we want to prove that two shapes in a graph make a rectangle, or not two, but if we want to prove that points on a graph make a rectangle, there's two ways we can go about it. If you want to prove something is a rectangle on a graph, you can prove that the opposite sides are congruent, and then prove that the diagonals are congruent using the distance formula. Remember, you use the distance formula to prove that segments are congruent. Or you can prove that opposite sides are congruent, and then you can prove that the lines are perpendicular using the slope formula. So I'm going to do both of them here, and then whatever one works for you, that can be the one you focus on. So let me do the first one first, the distance formula one first. So remember, if you want to prove that something's a rectangle, you can prove that the diagonals are congruent and that the opposite sides are congruent. So the first thing I would do is draw a quick sketch so I know kind of what my diagonals are and what my opposite sides are. So P is at negative 5, 3, so it's going to be somewhere, let's see, 1, 2, 3, 4, 5, 1, 2, 3. So P would be somewhere right there. Q would be 1, 1, so 1, 1. There's Q. R would be negative 1, negative 4, 1, 2, 3, 4. So there's R. And then S would be negative 7, 0. So 5, 6, 7. So S would be like right there. So I'm asking if this is a rectangle. It looks pretty rectangular, but let's just do it to be sure here. So I want to prove that opposite sides are congruent. So what are my opposite sides pairs? So I should probably mark that down first. My opposite sides would be PQ and SR. So PQ needs to match with SR. And SP and RQ. So SP, or PS I should say, PS should match with QR. So those are the opposite sides that I'm looking for. So I'm going to use the distance formula to figure out how long each side is, and then see if they're congruent. If you don't remember, the distance formula goes like this. It's x1 minus x2 squared plus y1 minus y2 squared, all square rooted. So it's kind of a long formula, but not too bad. It's kind of like the slope formula. That's where it's come from. So PQ. So PQ. So that would be the square root of, let's see, my x's in this case would be negative 5 minus 1 squared, plus my y's would be 3 minus negative 1 squared, all square rooted. And so if we do some mental math here, this would be negative 6, which squared would be 36. This would be, let's see, minus negative 1 would be plus 1, so this would be 4 squared, which would be 16. Added together, you get the square root of 52. Now, I don't know what this actually is because it's a weird decimal, but I'm just going to leave it as the square root of 52 and see if my partner here, which would be SR or RS, either one, this one right here, these two should give me the same result if they're congruent. So this should also be root 52 if they're congruent. So let's check. So for RS, so R and S, my x's would be negative 1 minus negative 7 squared plus negative 4 minus 0 squared. So let's see what this ends up here. This would be negative 1 plus 7, which would be 6 squared, which would be 36. This would be negative 4 squared, which would be 16, and that would also indeed give me root 52. So far, this first relationship checks out. So PQ is congruent to SR, which is good. Now I need to check the other pairs, so PS and QR. So let's do these real quick. So PS, so P and S. So my x's go first, so -5 minus -7 squared plus 3 minus 0 squared. Doing some mental math here, that'd be -5 plus 7, which would be 2 squared, which would be 4. It would be 3 squared, which is 9. And 4 squared plus 9 would end up giving me the square root of 13. So this would be root 13. And then QR, we'll hope is the same. So x is first, so 1 minus -1 squared plus y's, -1 minus -4 squared. Here equals, so let's see here, that'd be 2 squared, which is 4. This would be 5 plus -1, which would be 9. Oh, sorry, I was doing that wrong mental math there, my bad. This would be -1 plus 4, which would be -1 plus 4 is 3. 3 squared is 9. There we go. And then that would all equal out to be root 13. Okay. So opposite sides are then congruent. So we know the opposite sides are congruent. All right. Now that could mean that it's a parallelogram. We don't know it's a rectangle. So in order to make it a rectangle, we need to prove that after we know that this is true, after we know that the sides are all congruent, then we need to prove that the diagonals are congruent. So the diagonals in this case are SQ and PR, which by the way is why I graph them first. That way I know what my diagonal points are. So I need to prove that S to Q is the same as P to R. That will prove that it's not only a parallelogram, but it's a rectangle. So this right here proves that we have a parallelogram, this work right here. And now I need to prove it's a rectangle by proving that the diagonals are congruent. So I'm going to do the same thing with these sets of points down here and hope that they're congruent. So P to R. So S is first. P to R would be -5 and -1. Plus, let's see here, Y's would be 3 minus -4 squared. Let's see here, this would be -5 plus 1, which is -4 squared, which would be 16. This would be 7 squared, which is 49. And 16 plus 49, let's see here, that'd be 55, I believe. No, sorry, 65. Try doing that correctly here, just so I don't have to go back and do this whole thing over again. 16 plus 49. Yeah. So hopefully this will come out to be the same way. So QS. So Q and S, the x's first would be 1 and -7. So 1 minus -7 squared plus -1 minus 0 squared. Let's see here, that'd be that'd be 1 plus 7, which would be 8 squared, which would be 64. And then -1 minus 0 is -1 squared, which would be 1. And so we end up getting 65. And so those are my two answers, and they are indeed congruent. So overall, we'd say yes, this is a rectangle. Okay? Because not only are all sides, our opposite sides congruent, but the diagonals are also congruent to each other. Therefore, it has to be a rectangle, not just a parallelogram. So this is one way of doing it. You prove that all opposite sides are congruent, and then you prove that both diagonals are congruent. Okay? The other way of doing it is to prove that all opposite sides are congruent and to prove that all the angles are right angles. Now the question is, how do you prove that something's a right angle? Well, you use the slope formula. So I'm going to do the same problem, just with a different way here. I'm actually going to skip this part down here just because it's the same as the last part. So we already did this part in the previous answer, so you can look at that. But once you get that all sides are congruent, then you have to prove that the intersecting sides are perpendicular. So remember, our thing looks something like this. So P, Q, R, S. That was the orientation, if I remember correctly. Yep. So I want to prove that PS is perpendicular to SR. That way I know that they make a right angle. The way you prove that lines are perpendicular is that you check their slopes, and their slopes should be opposite reciprocal. So reciprocal means a flipped fraction. So for instance, if one of them has a slope of 3/5, to be perpendicular, the other one needs to have a slope of -5/3. So it's the opposite, which means it's negative, not positive. And it's the reciprocal, which means that it's a flipped fraction. 5 on bottom, now it's 5 on top. So that is what we're looking for in our slopes. If they're perpendicular, or if they're opposite reciprocals, then we know they make a right angle, and we need 4 of them. Because remember, all the angles need to be right angles. Technically, we only need 3, because if 3 of them are right angles, the 4th one has to be a right angle. But we should check all 4 just to be thorough about it. So we're just going to go through and check. So the first thing I would do is I would just list out all the slopes by themselves. So PS, SR, QR, and PQ. So I'm just going to list out the slopes as they are. And if you don't remember, the slope formula is y1 minus y2 over x1 minus x2. That's the slope formula. So for PS, again, my y's are 3 and 0. So this would be 3 minus 0 over my x's, which is negative 5 and negative 7. So negative 5 minus negative 7. That'd be 3 on top. This would be negative 5 plus 7, which would be positive 2. So 3 halves. So PS has a slope of 3 halves. Let's do SR. So SR. So my x's in this case are negative 7 and negative 1, and my y's are negative 4 and 0. So let's do the y's on top first, like we should be. So 0 for the s for y, minus negative 4 for the y for r. And then the x for s is negative 7. The x for r is negative 1. Remember, it's a minus negative, not just a minus. So this would end up being 4. Negative 7 plus 1 would end up being negative 6, which would reduce down to negative 2/3. Right? So for QR, again, y is on top. So y for q, y for r. So negative 1 minus negative 4. X for q, x for r. So 1 minus negative 1. Negative 1 plus 4 would be 3. Negative 1 minus negative 1, which is again is a plus 1, which would be 2. This would be 3 halves. And then PQ. Now, technically, we should know what this is anyway, because if we've proven that it's a parallelogram has opposite sides parallel. So technically, we don't need to check all 4. We just need to check 2 of them, because if 2 of them are perpendicular, then the other 2 have to be perpendicular because, again, the way the slopes work. But I'm just going to do all 4 just so you can get used to me seeing the slope formula here. So for those of you that know how to shorten it up, yes, there are some shortcuts here you can apply, but I just don't want to go into them right now just to make sure that I get the base form down. So y for p is 3, y for q is negative 1, so 3 minus negative 1. X for p and x for q, so negative 5 minus 1. Let's see, this would end up being 4 over negative 6, which is going to end up being negative 2/3. And again, this is what I was talking about. You can see that these are the same, and these are the same. And the reason is because it's a parallelogram. So PQ should be parallel to SR, and QR should be parallel to PS, and again, vice versa. So once I found the slope of these two, I automatically knew the slope of these two, because if I've proven that their sides are congruent already, then I know that the slopes have to be parallel. Again, you don't necessarily need to know that, but that is a shortcut you can take if you remember it. So now the goal is to make sure that the opposite sides are that the angles are all perpendicular. So PS and SR is my first right angle. So are those perpendicular? So where is this? So PS and SR. Written backwards here, but no big deal. So PS is 3 over 2 compared to SR, which is negative 2 over 3. So these are indeed opposite reciprocals of each other. So these are indeed perpendicular. So that is a right angle there. Good. Now we need to check the other ones. So what about this one right here? This one is QR and SR. So QR and SR. So QR is 3 halves. SR we already automatically know is negative 2/3. So that also checks out. So it's a right angle there. What about this one up here? PQ and QR. So PQ is negative 2/3 as a slope. QR is 3 halves as a slope. Those are indeed opposite reciprocals. The fraction is flipped, and one is positive and one is negative. So that would also check out. And the last one, you can probably tell, is going to be the same thing. PQ is negative 2/3. PS or SP, either one you want to say, is 3 halves. And once again, those are indeed opposite reciprocals, so those check out. So all 4 angles are opposite reciprocals. All 4 angles are perpendicular. Therefore, they're all right angles. So this would be, again, yes, this is a rectangle because all opposite sides are congruent and all angles are right angles. So that's another way of doing the same problem. So it depends on which ones you're more comfortable with. If you're more comfortable using the distance formula and just proving that sides are congruent, the first way we did. If you're more comfortable using the slope formula, which in my view is a little bit quicker, you just have to make sure that you pair up your lines correctly, then you can use the slope formula. If you notice that the first step is always the same, prove that the opposite sides are congruent. So you have to do this first, because this first part proves that it's a parallelogram, and then once you've proven it's a parallelogram, you take that extra step, proving that it's a rectangle, using either the slope formula like we did down here, or using the distance formula for the diagonals like we did down here. So that's your choice. That's it for this video. Hope you enjoyed it. Have a good day, night, or afternoon.